In this section of chapter 7, I would like to talk about electron shells, their sizes of atoms and ions, and electron configuration of ions. Electron shells are defined by completed n equals to 1 or n equals to 2. Now first shell would be 1s2, and second shell would be defined by 2s2 2p6. Third shell would be defined as 3s2 3p6. Now let's just think about very first shell 1s2, and the question is, if I have three different atoms, helium, neon, and argon, in which case 1s shell is going to be closest to the nucleus. Let me give you an idea how to come up with this answer. If you're focusing on the same shell, which is 1s shell, the size will be influenced by attractive force towards nucleus. So basically you need to look at what is the number of protons for helium, neon, and argon. If you look at periodic table, helium has 2 protons, so let's write down right beside helium plus 2. Neon, can you see neon? It's also a transitional, it is a element at the very end, noble gas. Neon has 10 protons or plus 10. Argon, element to the bottom of that, which has atomic number of protons 18. So in other words, even though we're looking at interaction of same shell, 1s shell with nucleus, but the nucleus has different number of protons. For helium is plus 2, neon is plus 10, and argon is plus 18. Can you think about in which case attractive force would be largest, and how is it going to affect the size of the electron shell? Now here we're looking at the same problem. 2 protons, I think it's 2p, we mean 2 protons, which is plus 2. So let's forget about p. Plus 10, plus 18. Now we have drawn about the same size now for 1s. So this is 1s. Now obviously we know that when you have the largest number of protons, there will be largest attraction for 1s electron. And in other words, that electron would be getting closest to the nucleus. So in other words, the size would be smallest for argon. Let's draw the actual what is going to happen. This is going to shrink even though you start with the same size to begin with. So argon would be the smallest, and then it would be neon, and then it would be helium. So keep this in mind, how size of a shell decreases with number of protons in the nucleus. Now same could be said about the second shell, which would be 2s2 2p6 shell. If you have more protons in the nucleus, that shell would get closer to the nucleus and would giving it a smaller size. In this slide, you're looking at electron density diagram. The first peak for neon represents 1s2 shell, and that peak means that's the largest probability of finding electron around that distance of 0.05 in case of neon. In case of helium, that 1s2 peak is at 0.3 angstrom. So that checks out what we just predicted. So 2s2 2p6 shell is at around 0.3 angstrom. So if we had 2s2 2p6 for, say, argon or xenon, that would be at a much shorter distance, because those atoms have a lot more protons in the nucleus, and there will be greater attraction for those electrons in this shells. Now we're going to discuss metals, nonmetals, and metalloids. If you look at periodic table, there is a borderline, and usually in most periodic tables they're shown with specific color, and that's metalloids. These elements have properties in between metals and nonmetals. On the left hand side of the borderline elements, these are the borderline elements. On the left hand side you have metals, and on the right hand side you have nonmetals. And the borderline elements are metalloids. The metals are shiny, they're good conductors of heat and electricity, they're malleable, you can bend a metal, it's not going to crack. Non-metals have just the opposite properties, so just non-metal. Shiny, not shiny, or dull. Good conductors, bad conductors for non-metals. Malleable, not malleable. It is going to crack when you try to bend it. Now here you're looking at the periodic table, and these are the metalloids. Let me show you here. These elements are metalloids, the borderline. So mostly you have metals. And nonmetals, among the nonmetals, mostly are on the right hand side of these borderline elements, except hydrogen, which is on the very top corner of the periodic table. So keep that in mind. If you remember the borderline elements, then obviously it will be a lot easier. And I assume that hydrogen is an exception in terms of the location in periodic table. Now about the sizes, now I can give you a couple of sizes and ask you which one will be bigger and which one will be smaller. So between sodium and lithium, they belong to the same group. So this is lithium and sodium. So which one will be bigger? To remember it, think about a hat. So in which this kind of a hat, the diameter of the hat increases as we're coming from right side to the left side, and either coming down. So with this in mind, now you can look at periodic table. As you are coming from right side to the left hand side of periodic table, elements are getting bigger and bigger. So this, as you are coming from this to this size, is getting bigger and bigger. As you are coming down, it's even getting bigger. So between sodium and lithium, you can see that sodium is toward the underneath lithium in periodic table. So sodium would be bigger than lithium. Now let's talk about sizes of ions. Now I can discuss sizes of ions based on several categories. Category number 1, ions with same number of protons but different number of electrons. Since it's same number of protons, it has to be same element. So think about Cl, chlorine, Cl plus, when I knock off one electron out of Cl. Cl minus, when I add extra electron to a neutral Cl. Cl2 minus, when I add 2 extra electrons. Now the question is, how do I predict their sizes when we have this kind of ions and neutral atom? Now these are the factors you need to consider. Proton-electron attraction, that tends to give a smaller size. If a larger proton-electron attraction, when you're comparing, it would give a smaller size. Electron-electron repulsion, that tends to give a larger size. Now, in case of all these different chlorine atoms and ions, number of proton is the same in each case. So it's the electron-electron repulsion that would determine the size of all these ions. Now, out of all these ions, of course, number of proton is the same because it's the same element, so that's not a determining factor. But number of electron would be maximum for Cl2 minus. And Cl2 minus having the largest number of electrons, there'd be a lot of repulsive forces between all these electrons, and they would spread out as far as possible. And these electrons determine the size of ions. So largest one would be Cl2 minus, then Cl minus, then Cl, and Cl plus would be the smallest because it has the fewest number of electrons. Now we're looking at second types of problems. In this case, we have, like, for example, neon, sodium plus, F minus, O2 minus. First, we need to find out how they're similar and how they're different in terms of protons and electrons. Now, if you look at the location in periodic table and count the number of electrons, neon would be 1s2, 2s2, 2p6. So that has 10 electrons. So neon has 10 electrons. What about sodium plus? Sodium has 11. So if you knock off 1, so that would also have 10 electrons. So in each case, F minus, no, F would have 9 electrons, F minus would have 10 electrons. So O2 minus, O has 8 electrons, O2 minus would have 10 electrons. So they all have the same electron configuration. And they're called isoelectronic, having same electron configuration of 1s2, 2s2, 2p6. So in this case, these ions and atom have the same number of electrons, but different number of protons. So keep this in mind. The number of protons are not the same. Now, in case of neon, how many protons we have? Let's write down number of protons on the top. Neon has 10 protons plus 10. Sodium has atomic number 11 if you look at periodic table. So atomic number means number of protons, 11. Fluorine has 9. Plus or minus fluorine doesn't make any difference in number of protons. As long as it is fluorine, it has to have same number of protons, which is 9. Oxygen has 8 protons, so that's plus 8. So even though in each case we have 10 electrons, electron repulsion factor is the same, but the attractive factor towards protons is not the same. Sodium having the largest number of protons would show the largest attraction. So in this case, electrons would get closer to the sodium nucleus. In other words, sodium plus would get the smallest size. In case of oxygen, the charge is the smallest, so attractive force is the smallest, so that would give the largest size to O2 minus. So keep this in mind. You'll have to look at both proton-electron attraction and electron-electron repulsion. When we have the same number of electrons, then our contributing factor towards the size would be proton-electron attraction. And you look for the largest number of protons. That makes the size the smallest. The third kind of problem deals with ions from the same group in periodic table. Then it follows the same trend as neutral element. That means as you're coming from right to the left, it gradually gets bigger. As we are going from top to the bottom, it's getting even bigger. So considering that, I minus would be the largest, because if you look at periodic table, I minus is toward the bottom, and as you go to the top, like I minus, then Br minus, then Cl minus, then F minus. So that's how you can determine the sizes. So I minus is the largest and F minus is the smallest among these given ions. So keep that in mind when both protons and electrons are changing, but by looking at periodic table, you can have an idea about the sizes of these ions. Let's work on problem number 35, A and D, page 281, Brown and LeMay book, 12th edition. Now, question is, considering the isoelectronic ions, they're already telling you that these are isoelectronic. Isoelectronic means same electron configuration. So it's going to, let's first write down those two ions, Cl minus and K plus. Okay. Now, how is it isoelectronic? If you write down electron configuration or count number of electrons, either way you get the same information. So you can write down as neon configuration followed by, go to the third line, make sure you have a periodic table in front of you. That would help. For Cl is 3s2 3p5, but Cl minus has extra electrons, so it'd be 6. For neutral potassium is going to be neon configuration 3s2 3p6 4s1, but for K plus you're removing that electron from 4s, so you have neon configuration 3s2 3p6. So they are isoelectronic. Now in terms of number of electrons, it would be 18 electrons. Okay, now the question is, which ion is smaller? Let's first write down number of protons. Same electrons, so electron-electron repulsion would be the same in both cases. So determining factor of the size would be proton-electron attraction, and that would depend upon number of protons in the nucleus. So again, look at periodic table. You'd see that Cl has 17 protons, so I'm going to write down as plus 17 for Cl. Cl minus doesn't change, because as long as you're dealing with Cl, Cl minus, Cl plus, it's all the same number of protons, which is 17, because these are characteristic feature of elements. And potassium plus, potassium has 19, so that's plus 19. So obviously, proton-electron attraction will be greater for potassium, having 19 protons attracting all these 18 electrons. So size would be smallest for K plus. So smallest, and Cl minus would be the larger ion. So that's part 35, part A. In part D, it is related to isoelectronic ions, which we are already dealing with, Cl minus K plus. How are effective nuclear charge and ionic radius related? Now we already discussed this a number of times. First thing is why they're related this way. Because screening factor or shielding effect is the same, because you have the same number of electrons. So electrons, inner electrons, that's going to shield the nuclear charge, and that is going to be the same for both Cl minus or K plus or any isoelectronic atoms or ions. So shielding effect is not going to make the difference. So difference would be due to number of protons in the nucleus. So if you have a larger number of protons, so let me write down this expression, Z effective equals to atomic number minus the shielding effect. Now this is the same for isoelectronic. For isoelectronic. So as Z is increased, effective nuclear charge is going to increase. And that's what you're actually seeing. So in case of any ion with larger number of protons, the effective nuclear charge is also be greatest, and the outer electrons are going to experience a larger attractive force, and they would get closer to the nucleus and the size would get smaller. So as number of protons is increased in the nucleus, the size is going to get smaller. Now let's go over another problem, 7.47C, page 282. This is on electron configuration of ions. Now, here we're going to do 47C. And now let me write down that question. 47C is about electron configuration of Mn2+. It's good to have periodic table in front of you when you are taking a test or working on a homework problem. That way your understanding would be a lot better. If I were you, I'm going to first write down electron configuration of the neutral, forgetting about Mn2 plus. So first write down Mn, and you can find out this Mn is a transition element, so it's going to be here. Vanadium, chromium, and manganese. That's where you. Now let's write down electron configuration. I'm going to write down just to write down in a briefly, rather than writing down from the very beginning 1:2, 2:2p6 and all those things. Let's write down argon configuration. So argon configuration in bracket, and then you come to the fourth line. Remember, the fourth line starts with 4s. 4s2, you are done with subshell s, and then it will be line number -1 because we are getting into transition elements. And so line number is 4. 4 minus 1 is 3. Let's count. 1, 2, 3, 4, 5. Or you can see the d number on the d orbitals that I have written down. So it's going to be 3d5. That's manganese. Now when you get manganese 2 plus, it behaves a little differently than other elements and ions. Here those two electrons would not go from d orbitals, rather it would go from nearest s subshell. So it's going to be Ar 3d5. So keep that in mind because this is different in case of transition elements. So keep this in mind for transition elements. When you get ions, first remove the electron from nearest s before you remove from d. If I had taken out another electron, if I had Mn3 plus, then third electron would go from d, 3d in this case.